So our question today is, does God play dice? And it's an interesting question. And I'll mention, like I did before, when I say God, I don't necessarily mean a human or personal God or God with a body. I just mean what upholds this universe, the physics of it, whatever is supporting the physics, keeping them upheld, keeping them true. So the question is, does God play dice? And Einstein, and of course all the physicists in the past, especially the ones in the early 1900s that were dealing with what eventually became quantum mechanics, were curious as to, there's a long debate between Bohr and Einstein whether quantum theory was a good way to describe what's occurring, or it actually described the underlying processes. Because essentially, you can measure some kind of quantum system, or just a state of a system, like the spin of an electron, and it'll be up one moment and it'll be down the next, and it's essentially 50% up, 50% down. So it's a probability distribution. And the issue with quantum theory is that sampling, is that description of the system as 50% one eigenvector and 50% the other eigenvector, the up and the down, and all possible linear combinations of them. Is that the reality, or is that conveniently describe the macroscopic behavior? So one thought is, well, Einstein had mentioned that, and it was a common thought at the time, well, what if there's this elaborate machinery that, not necessarily mechanical, but this large mechanism by which the spin is changing. Maybe it's changing so quickly, right, that there's no way we can be fine enough to zone in on that very tiny frequency. For example, let's say I had something, right, and it's going, 10,000 times per second up and down. Clearly, we can zone in on it, right, with our current technology. Even a high-speed camera, it's just 10,000 times a second is nothing. It's a very, it's a fast frequency, but it's really nothing in the grand scheme of things. So, we could definitely zone in on that intervals. It would always be that, right? If at 10,000 times per second. Now, let's say we're talking about something going, a billion times per second oscillating. Even if we could get something that could oscillate at the same rate, right? Let's say we get the camera or whatever's prodding it to go up and down the same rate, which would be very hard in the first place. But assuming we could get something going close to that rate, there's still that issue that at that rate, if you have any tiny inconsistency with your equipment, it's just going to resort to randomness. So that's the issue, and it's a large issue in quantum mechanics, all the time, saying, measuring problem, right? And is it the measuring? For a long time, actually, there's this von Neumann, very famous mathematician and physicist, had a theory with Wigner. So this other famous physicist, I forget his first name, was it Eugene Wigner, right? So I'm looking at the Wikipedia right now. So this von Neumann-Wigner interpretation, consciousness causes collapse of the wave function in quantum mechanics. And, the idea was that there's this causal chain from when you measure some aspect of a quantum system, and then finally the measurement gets read by a person, and ultimately, that there's a final result from that probability distribution, right? That spin is half up, half down, and eventually some measurement happens, and then someone reads it, and there's just a binary result. It's either it was up or it was down, right? And so the question is, along that causal chain, right, from the actual particle, or maybe it's not even a particle, right? You could say from the wave or whatever it's acting like, right? From that is some interaction with the measuring device. The measuring device has some recording apparatus, and the recording apparatus, makes the marks, and then a person finally reads it. And, the question is, where did the collapse occur? So what we think now is this Wigner, von Neumann-Wigner interpretation doesn't hold up. We think that any system that measures another system will inherently cause collapse. And there doesn't need to be a human around for that to be the case. So that's sort of been taken out, but there's still some level of validity to the idea, because we can't exactly erase ourselves from the equation. At some point, we need to find out, what a result is, and then we ask ourselves, well, by finding out what the result was, did we somehow collapse the whole chain? Was it like unevaluated, what we call lazy evaluation and programming? Meaning, you have this huge computation and it doesn't even get ran until something asks for the value. So, in any case, where were we? So we're talking about systems and quantum systems. And we're asking, Einstein asked God, does God play dice? And imagine there might be some elaborate mechanism. Maybe it's, like I said, moving, the frequency of it is so fast, right? And that would make it, that would make essentially our ability to just even see that going on very, very difficult, maybe even impossible. And of course, the mechanism might be extremely small as well. There's a lot of things that factor in, and if you didn't know this, so essentially the smaller you want to probe, right? Like particle accelerators, for example, they want to smash two small particles together, maybe, whatever, two electrons, proton, or maybe two gamma ray photons. It's, called photon annihilation. They try to smash two things together. And what happens is, if you really want to see these results from the more bound particles, the ones that are really small and held together, like the quarks and whatnot, muons and whatnot, you'll need to put a ton of force into just a couple single particles. I mean, we're talking about two particles, not, two elements or whatever, two pieces of something, just two fucking tiny particles, but they've been accelerated with magnetic fields to go so quick, and they get them going around, and they finally merge the trajectory, so they smash. But that takes a tremendous amount of energy, and the reason is, the smaller you want to go, the more energy you need to sort of get precision and sort of get over those energy wells. To take two things apart that are extremely small, these are fundamental forces of the universe. Strong force is, well, extremely strong. You can't even really separate quarks because the force is so strong that as you pull them apart, the force grows and grows and grows. So makes it. It's not like magnets. Magnets you start pulling apart and the force weakens. Strong force opposite. But in any case, the smaller you want to probe, or the higher frequencies you want to try to get a handle on what a pattern might be, what's going on, essentially the more energy you need, and the harder it is to get to those levels. So that idea that Einstein says there might be a mechanism, but the mechanism is so small or so quick that we can't exactly probe it at our current level of technology. And even with possible technology, it might take a sun's worth of energy at a single time in a particle accelerator, something like that, to see what's going on. So as far as we can understand that quantum theory, regardless of what might be going on inside these quantum systems, we basically think that the quantum theory, at least the probability distribution, describes it well enough. So question is, does God play dice? Is it random or is it deterministic? So if we want to analyze this from a philosophical point of view, we have to sort of talk about what it is to be random. And that brings us to something called Kolmogorov Complexity. It might be slaughtering the name, but let me pull it up on Wikipedia. So Russian mathematician Kolmogorov, he basically came up with some measures on how to detect whether something's random. Obviously, there's a lot of different measures for randomness, and there's also context, which matters, right? Like Bayesian priors and whatever. It depends what you're looking at. I mean, you could name a number and ask, is this random? And well, obviously with the context, it's random because you set a random number, but nothing is random intrinsically, right? Something is only random. A distribution could be random, but a single thing can't really be random. You have to include how it was generated. So the generation is almost like talking about what the distribution is, right? So in any case, ask, okay, indeterminism, right? I want to talk about, God having dice. What would that even mean? Well, if quantum theory is really correct, if that's the nature of the universe, then, nature, God has a random number generator, right? He's able to come up with random values in some way. And the question is, it's sort of this catch-22, and it's always this kind of mindfuck with the universe or anything that sort of relates to sort of the questions about it, is, well, if it has a random number generator, how is that random number generator made? You say, okay, well, we understand determinism, right? We'd say God is essentially nature, essentially a program, right? A big, large program. A lot of directions, because we very well understand what a direction is. But then you talk about indeterminism, and the unfortunate part is all the randomness that we know in our universe, at least even what we want to use, like dice, and just you can plug in a card with radioactive material and into your computer to get random numbers. Some gambling sites do this. They have fission material, or not fission, just decaying material, and that generates random, when it decays, it's sort of random. So that's how they get the random numbers. There's other methods, like Intel has an RD-RAND instruction on their CPU that uses electrical arc, high voltage, and then sort of samples the fluctuations in the voltage. So there's a lot of other ways, but they're all mostly borrowing randomness from the physical nature of the universe. So they're sort of borrowing that quantum randomness. And not always, let's say, quantum, it just, randomness of just complexity. The universe is so complex. Local pockets are affected by global pockets, and you have the butterfly wing idea, right? So they want to sample pieces of that. But a lot of these things, like let's say the voltage one, the environment's not playing as much a part as some of the quantum randomness, and sort of even the decay is sort of dictated by this quantum randomness. So you get randomness a lot of ways. You roll a dice, and there's the complexity sort of randomness. There's just so many factors, and we can't compute all the factors. And I could give that classic thing. It was like, something may not really be random, but it's so complex that it appears random. And that's the crux of this whole thing, right? Question is quantum theory really random, or is it so complex, the underlying implementation, the underlying reality, that it appears random? So if we talk about God having some sort of randomness, we have to grant it to him. almost like he essentially has an oracle, right? He outsources his randomness to India. He needs a telemarket, whatever. So he needed randomness, and he hired something else for it. Because the only way we can explain it, if he didn't outsource it, right? If nature didn't outsource randomness, and nature's main method is determinism, right? Just some instructions, some rules, then how did he build randomness from rules? And that brings us to what I was talking about before. Let's bring that Wikipedia up again. Kolmogorov complexity. So one thing that's really special that we've sort of studied in mathematics, but still has a lot of an enigma to it and shrouded mystery, is algorithmically random sequences. And a measure of how random a sequence is what's called Kolmogorov complexity. So if we have a sequence of numbers, right, or just let's say a corpus, a book of text, right, it translates to numbers anyways. If you know what's called, ASCII, you can say A is 1, B is 2. Computers use different code, but any kind of string can be translated to numbers. So let's say you have a string, chapter of a book, and you want to know how random it is. And obviously you could look at it and just see if looks like there's more of a pattern or less of a pattern. We know if someone says yes, 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 it doesn't seem very random. All the same symbol, right? All the same choice. So Kolmogorov came up with this idea that if you can write a computer program that would generate the members of a sequence, that will generate the sequence, right? The whole sequence, then the Kolmogorov complexity is the length of that program that generates the sequence. So the idea is that let's say I had 100 yeses in a row, right? Well, in the right language, most languages, programming languages, we could even talk about English actually, doesn't need to necessarily be a computer language. It could be just referring to a grammatical language. The idea was mainly, though, it was a computational idea, because there's problems when you allow normal language. There's paradoxes like the shortest, the word with the shortest, the number with the shortest, the number of numbers that have a description shorter than 20 characters or something. And that what I just said has, less than 20 characters. So whatever number that is needs to be the shortest. So if that were the shortest, but then it wasn't the shortest because it referred to it. So there's a lot of paradoxes with actual English. When you have a programming language, you really can't get that self-referential and ambiguity. So basically, it's Kolmogorov complexity for that. Let's say 100 yeses, I could just write repeat yes 100 times. In Perl, it would just be yes x 100. That's a really short program, right? And even if I made it 1,000 yeses, the program only goes by a single character. Instead of 100, I put 1,000. I add one more zero. So the thing is, when you have an actually, random sequence, or at least what we want to look at with Kolmogorov complexity and what we feel is random. Excuse me. We'll essentially have to just put the fucking string in and put print, right? So if I had, let's say, just white noise, just random, like I got off the radioactive decay, huge block of it. Yeah, I could search maybe for ways to compress it, right? But randomness is usually not very compressible, actually, for the reasons we're talking about. But even if I could compress it a little bit, it's not going to help much. I could search maybe for something that might generate it, like a mathematical sequence, but the idea is that with compression theory is that if you compress noise, then you can't compress other things well. So there's no like, if you search for a math formula, the odds are that you're not going to find one if the sequence that you're looking to find something convenient for is really, really long. The longer it gets, the less likely you're going to find a formula for it. So ultimately, you know, you have this string, and it's, you know, you got it from, let's say, the radioactive decay, and the only way to really put in a program is just print and then the actual literal data. So it didn't get any shorter, and it maybe got longer by having a printed front, but that's constant, so that's kind of irrelevant. The idea is that for a random sequence, the Kolmogorov complexity should be approximately the length of the sequence itself, with whatever constant size of the instruction to actually output it. So we would just say, you know, Kolmogorov complexity of a supposed random string is about the length of string, right? So we have this Kolmogorov complexity, and the question is, right, we were talking about how God may not have a method for indeterminism unless he outsources it. He doesn't have a random number generator. At least we can't even imagine how he could build it, because all we know is about determinism, right? And if he's using indeterminism, then that has to be from something else, right? Unless we take the point of view that even his method of indeterminism is from determinism. And it's sort of confounding, because most people think of randomness and they think it's almost like a different breed than order. But the truth is that many things that come from convenient and ordered formulas, like fractals, would be impossible to trace back. So there's this idea that if you have an infinite sample space and you, let's say, just choose one piece of it, it's going to be impossible to trace where it came from. For example, we zoom in to a fractal, let's say the Mandelbrot set. We zoom in, we zoom in, we zoom in. We find some point on it, right? We don't need to really zoom in. We just need to specify high precision. Let's say we look at, you know, pi, right? You point under pi plus, let's say, 0i. Actually, they may be outside the Mandelbrot set. We have to look at like 1.5 plus 1.5i. You know, we go in there and we see the details, and we and for every time we need a new random number, we just zoom in a little bit and take a piece. Now, if someone knew that we use the Mandelbrot set, right? If we're giving numbers, let's say we're in the let's say it's like the Chinese room experiment by Searle. Say we're in a room and we're looking at the Mandelbrot set, and we'll pass out random numbers from under the door, pass them out to the people outside, and we're getting them from the fractal. We're just zooming in. We chose a very specific point, and we zoomed in, you know, very deep. We had a high precision. We knew where the exclusions were, you know, what's in the set, what's not, and we fooled around, and we went into some very, very offshoot of a branch. Now, the question is, if someone doesn't know that we used the Mandelbrot set, do they have a chance ever of finding out the method to the madness, right? If there are an infinite number of universal systems that essentially can generate every random sequence from recursion, right? Certain fractals, or even rather the Riemann zeta function is said to be universal. It has universality because every continuous function occurs inside of it. So there's craziness like that, you know, and that's not even really a fractal. Of course, it has infinite detail though. But so I guess it has fractal dimension, I guess you would say, but it's not conventional, not conventionally considered fractal. But yeah, you have this issue when it comes to God's dice, and it's whether if we say, hey, it's real randomness, he uses randomness, we don't know how to explain how he creates it. We're just stuck. We just have to see that he has some ingredient, special sauce, randomness. And to me, it's not very satisfying to say, here's randomness. I think it's more satisfying even to give him some other, special, I guess, ability, like, for example, hypercomputation. So if we don't grant him randomness, right? We say he has to build his randomness. Maybe he uses a fractal, or maybe he uses an infinite polynomial with an infinite number of weights that we aren't going to be privy to. But again, there's a problem with that, because where's he getting all the weights from? Is he using a different formula for it? Is he deciding them randomly? Because, well, how is he supposed to decide things randomly if he hasn't invented his random number generator yet? Again, you can't build something if it requires the same ingredient that you're building. So in any case, though, hypercomputation sort of gives him something that lets him maybe build something that we'll never even be able to touch, let alone even if we knew how it was done. So, there's certain questions about, like, Chaplin's constant, or Chatlin. I always see these names terrible. Really should, I guess, Gregory Chaitin, right? Gregory Chaitin. So if we look at Chaitin's constant, it's essentially a transcendental number. It's the probability that a randomly chosen program will halt. And it's different for every language, but the idea is we'll never be able to compute it, because it requires us to go through every single program that could exist. But as we know, programs and the halting problem, the universality of programs sort of puts a damper on that. Programs could do anything. We don't know what they do until we run them. There's no shortcuts. So that constant, we'll never be able to know. And the question is, well, if he has the ability to do hypercomputation, which means do an infinite number of things in a finite level of time, or not even talking about time, but if he can do an infinite number of things while we have finite time, right, then he can use that every second while he's running the physics, great animation, right, the great animator. So while he's animating everything, he might be doing hypercomputation. Especially, we know he's able to do hypercomputation if the universe is infinite. And even if it's closed, like a torus or a sphere, closed topology, he can still be using hypercomputation. Maybe the amount of the density of energy has infinite fidelity. Maybe quantum waves, quantum waves have infinite fidelity. There's a lot of things we think are analog, infinitely fine. But then we have Planck lengths and Planck energy, and even have suspected highest frequency for a photon, things like that. So we're not really sure whether there's this fidelity or it's rough. And even space-time, there's the idea that it could be a foam at the quantum level. That's what quantum gravity sort of, loop quantum gravity has, like a spin foam. In any case, if we get back to the point at hand, it'd say he could use hypercomputation, right? And we'd still be able to understand that. I sort of think that's sort of granting him an ability that can be understood We already know what computation is. We know what hypercomputation is, we just can't do it, right? Randomness, on the other hand, we really don't know what it is except the fact that we can borrow it from this universe. The only randomness that we know what it is a real randomness, or at least can't be considered the same, the algorithmic randomness, the Kolmogorov Complexity randomness, where you're just saying, hey, if I'm given this sequence, I can't ever figure it out, even if it came from some type of chaotic system. So the question is, does God, what does he use if he's going to use dice? What's the best candidates, at least as our mathematics tells us? It seems like the best candidates are chaotic systems, recursive systems that feed on previous input. There's simple systems like linear congruential generators that loop around every so often for a certain period, depending on the size of the numbers that are being used. They'll go to like 2 to the 50th, and then it'll come back and they'll repeat. There's things like fractals, though, that have infinite detail. Yes, they repeat in some areas, but they are infinitely, you can always take a different route. So there's always a way not to end up seeing the same thing, but there's always a way to get back to the original. The Mandelbrot contains an infinite number of itself, which is fascinating, right? So it's one way to sort of, to anchor down what's going on. And the other way to explain the randomness, which I like a lot, is this notion of a fractal universe. So inside the electron, right, any kind of small particles, it's possible that Terence McKenna, if you know, is big acid head, but also like Carl Jung, and it was quite smart, had a lot of interesting ideas, did a lot of talking, and wrote some books. And he had this idea of machine elves. And that's because he did a lot of DMT, and people see elves and stuff like that. Personally, I've never seen them, but these machine elves, I sort of started thinking about it one night, and it kind of dawned on me that I think what he really meant, even if he didn't know it himself, maybe what people are seeing, I don't know if it could be related. I'm not that I was going to say kooky, but I don't want to be judgmental or sort of demeaning. But this idea of machine elves made me realize that the universe, the one of the aesthetics of it, when I say aesthetics, I mean just defining laws, defining permanent thing, defining permanent values of it. One of those values could be activity at every level. So this would also imply that the universe is fractal. It has no bottom. It has no top. There's no macro scale. There's no micro scale. So even though some people subscribe to the philosophy that we're just pieces of shit on a planet that's rotating around the sun in a galaxy, Milky Way galaxy, inside next to the Andromeda galaxy, and then so on and so forth. We're just insignificant, right? It might be the case, at least in a fractal universe, that there's no scale at all, because there's an infinite number of things smaller than us. There's an infinite number of things larger than us. So how do we say we're medium or small or large? We can't. And especially when you start thinking about this idea of machine elves, sort of beautiful in a way, activity everywhere. So let me explain. This relates to the randomness, because you think about, let's say, the electron, or these very tiny particles that we physics currently kind of claims that these things are indivisible, especially a photon, right? Yes, it can be a wave and a particle, but a photon itself, right, the fine structure constant, photon structure, function and whatnot, there's no structure to the inside of a photon. It's said to be atomic. It's a single particle, right? You could go through a standard model, and there's these, fundamental particles that we think many of them are indivisible. They're as low as it gets. You don't get anything inside of them. The only kind of interesting things you get are, like for the photon, because it interacts with electromagnetic, stuff comes out of its trail, things like that. There's drag on it, and a lot of things come out of it just because of its existence with everything else. But we don't think there's anything inside of it. But think about this, right? Let's say inside of this photon, there's an entire universe of smaller things, an infinite number, because remember, it's infinite activities everywhere, infinite detail, fractal universe. But remember that this photon has this macroscopic behavior, right? Spin up, spin down, polarization, all these different things, right? And where's that randomness coming from? Why is it changing? Well, if there's universes inside of it, right? There's smaller things inside of it. I shouldn't say universes. I just mean this microcosm that we're sort of unaware of, right? But we know that that there's all these observables that are erratic, that are changing quite often, right? Changing at a speed that even our finest instruments cannot find it to be the same, right? Once picosecond, it's one value. The next picosecond is another. And of course, when you measure it, you also change it. It will affect it. So that doesn't help either. Or you may just collapse the wave function and it just stays at that certain thing. So in any case, inside of this, in all these particles, there's essentially, why wouldn't intelligent life exist? You've got to ask. If there are constructs of this universe, materials, right, or just energy manifested, assume energy is infinitely divisible, that it is wave-like, right, in a indivisible level, that Planck radiation and the highest frequency and the lowest, let's see if I can pull this up. So it's called so we have ultra high energy gamma rays, but if I can find it, oh, here it is. So highest possible frequency of a photon based on Planck time, right? So it'd be 1 over Planck time. So they're saying Planck time is the time required for light to travel a Planck length. So essentially, Planck frequency, the highest frequency of photon is possibly thought to be just this Planck distance, right? And the distance at which quantum effects sort of manifest. And that may be wrong, right? Quantum effects may manifest because there's all this intelligent and vital things going on at a smaller scale. And sort of this quantum randomness is just a sample of that. All these lives and all these, essentially just this microcosm in infinite depth of activity, just grouped together, percolating, bubbling, and generating a single value, right? Maybe just spin up or spin down. So we must be machine elves too, if that's the case. You know, for the behemoths made out of our galaxies, right? Maybe, you know, they don't care so much about electromagnetism. They're more concerned with gravity. Different forces have different forces are weaker or stronger at certain scales. Light takes a long time to travel throughout a galaxy. So, well, more than a galaxy, but, you know, just the bigger these things get, the more they're going to be dictated by certain forces over other forces. But the idea would be that there's an infinite amount of detail, and it doesn't matter if you move slow, right? As long as things don't change while you're moving. So the cosmological structures change to surprise whatever being's made out of them? No, they don't change quick enough in that manner. So sort of what matters to something, some behemoth, you know, colossus made out of a couple galaxies or more, doesn't matter, you know, to us. And what we do is just generating the ones and zeros for his fundamental particles, what he, you know, can't probe into. Even if he cared, he might not be able to ever detect us because it's not within his level of instrumentation. So you do have this this interesting idea of that at least to me, so it says that it's not that we're not important. It's not that we're important. It's not that we're the smallest, the largest, or we're at a certain scale, but like everything is required. All these machine elves, us, right? What's inside our electrons, what's inside those machine elves, as tinier and tinier and tinier Russian nesting dolls. That's all required for the upper level and even the lower level. It's all required for each other. And you sort of can ask yourself, well, you know, there's the simulation hypothesis, and if the universe, right, has no bottom level, then you say, well, where does the value then finally fold, right? If there's all these things happening inside the electron, right, infinitely detailed, there's never a smallest thing. You can keep going and find, you know, the life of this tiny being and tinier being and tinier being, and they're all probably intelligent. They may be a lot smarter than us even, but their scale, we're never going to really probably know about them. But in any case, we have to ask, right? How does the value finally pop out? How does it come out if it involves an infinite number of parameters? Well, the answer might be what we discussed before, a hypercomputation. Or maybe it's not hypercomputation, but certainly we can't do the same thing. We can't resolve a fractal. We can zoom into it, but we can't resolve it infinitely. We can't show the real thing, unfortunately. I don't know if people know this. We never show the real Mandelbrot. We show it to a certain fidelity. We know what's not in the set, right? With certain threshold values, like 2, this region of a circle radius 2, because and there's bailout values. If it gets higher than, well, 2's the bailout value. It gets higher than 2. And then we'll do a number of max iterations where we keep plugging in the number into itself. And if it goes beyond 2, then we'll say, okay, it's not in the Mandelbrot set. And based on how many iterations it took to fail, we color it. But everything that's colored, we're not sure if it's in the set. Or sorry, my apologies. We're not sure it's not in the set. We know what's in the set, but anything that's not in the set, we're not exactly positive about it, depending on what we set our bailout value and max iterations. It's heuristic. So we'd only be able to show the real thing if we had the ability to run an infinite number of computations in a finite number of time. So you have all these ideas that mesh together. You have the God's dice, the randomness of quantum physics, right? Quantum mechanics, and just of nature itself. Is the determinism, or is the randomness just chaotic, deterministic, procedure? Is it using a fractal or some type of recursive equation, like the digits of pi, possibly? Something from an infinite space that is algorithmically random. Is that what it uses? Or is it just a secret ingredient, right? Or is it hypercomputation with maybe one or the other? An infinite number of computations in a finite number of time. That we can understand. It's a special ingredient, but one we understand. To just grant randomness is hard to do, because the only randomness we actually know, we just take from this universe, right? And then we go down to the related thing, which is maybe the universe is infinitely detailed, fractal, and everything that we see as quantum noise is really just those infinite details percolating to the surface. And it's hard to imagine how that could take place, but we do get some sort of notions on how that could take place. Sort of just with this idea of like Hilbert's hotel. If you have an infinite, number of hotel rooms, and all of them are taken if all of them are taken, right? You just shift them to the right. Now you have a hotel at number 1, and you said number 1, whoever was in room 1 went to 2, whoever was in room 2 went to 3, and so on and so forth. 3 went to 4. So you've shifted them. Now you have a free hotel room on number 1. Maybe smaller details shift, and then you get that, sampling that creates the macroscopic jitter. Or maybe, I was going to say maybe the larger details also shift the other way. So you get the jitter and the smaller from the larger, but I would think it smaller comes to larger would make more sense, because that's essentially, I know not every quantum system is small, but that's sort of the basis of what quantum mechanics was about, these very small particles having jitter. So I don't know the answer, but I thought these were interesting thoughts to discuss. And I am working on a life simulation, sort of with cellular automata, just based on collision-based computing. Just the idea that maybe if have the right dynamics thermodynamically, you can see what would result. Sort of playing out chaos. Well, have a good one.